statistics is. You must have taken 2023. So what is statistics?
I don't know, it's really broad. It's hard to say, but I was just thinking along the lines of the likelihood of something or some event happening in different mathematical forms.
Okay, so statistics, likelihood of events. Perhaps I should say study of likelihood of events, because it is a field. What else?
The field associated with managing data and coming up with conclusions based on it.
So study of likelihood of events, field associated with data management and inference. Anything else? We'll take one more statement. Okay. I underline these two, likelihood and inference, for a reason. There is a difference when we say, oh, something is going to happen and something is likely to happen. Do you agree?
Yeah.
Because one is deterministic, it is certain, you know it is going to happen. Great. The other, not deterministic, it's random, so we want to understand the chances that it would happen. So chance, likelihood, probability, they're all the same. Study of likelihood of events, broad, theoretically. But reasonable definition. Field associated with data management and inference. Data management is one side where, you know, a computer scientist can manage data and hand over the data to you. But the key part here is inference. Yes, you have a whole lot of data, but can you learn something from that data? And statistics offers tools to infer from the data. One of the simplest ways to, or the fundamental way to infer from an experiment or a study, observational study. The inference is done using modeling. So that is the ultimate objective, which is to come up with models that we can use to infer about a random process. Okay. In this class, this is of importance because we will talk about probability mass functions, cumulative distribution functions, and different densities and distributions. All of those come back to that fundamental concept of modeling. We want to know the distribution of data for data that comes from a specific experiment or observational study so that we can model and infer. So that's where we are going. And one of the fundamental things that we need in statistics is probability. So the course is called Probability and Statistics for a reason. The entire field of statistics depends on probability. Now, what is probability?
Chance of a given event occurring, like, just a chance of a particular event occurring, given what you know about the situation.
The chance of a particular event?
Happens, yeah.
Okay, anything else?
Theory behind statistics.
The theory behind statistics. Good deduction. It is a measure of uncertainty or randomness. As I mentioned earlier, we consider non-deterministic processes, in other words, random processes in the field of statistics. So probability is a measure that lies behind, that is used to measure uncertainty or randomness, or we're trying to quantify uncertainty or randomness. I put measure within double quotes for a reason. There is a difference between a number and a measure. Analysis might cover it. I don't. But a measure is something that is defined over sets. Right? So a number is a number, but when we say a measure from a theoretical standpoint, a measure is something that is defined over a set. So if you have a bunch of sets, then we use a measure to define it. This is getting too much into theory. If you want, you can look into Borel measure, Lebesgue measure. By all means, probability is the Lebesgue measure. But it's advanced. Even I don't get into measure theory because it's out there. So it's very theoretical. But we call it the measure because we are defining over a set. That brings us to another question. What is a set?
Well, fundamentally, it's a collection of items.
A collection of items.
Yeah.
What sort of items?
Depends.
It depends. Okay. Can you give me an example of a set?
So there's the empty set, which is just nothing. It contains something that contains nothing.
Okay. Empty set.
And a set of 1, set of 2, set of 3.
What else?
Set of all real numbers.
Set of all real numbers. Okay, we're going too theoretical, too far.
Oh,
Something very practical.
the letters of the alphabet.
Huh?
The letters of the alphabet.
Letters of the alphabet. So
A.
A, B, C, D, dot, dot, dot. Well, two Z. So empty set. What's an empty set? And you have letters of the alphabet. That is a set. Can you think of anything else?
So numbers. A set of numbers.
Set of numbers. It could be anything. So perhaps just say 2, 17, 35, 47, 73. A sample. What is a sample in statistics?
A smaller group of a set.
Smaller group of a set. We will address that soon, but she is correct. But in simpler terms,
Subset of the population.
you're kind of going along with, you guys are correct, but I want something even simpler.
Group of people you find data from, or you take data from.
It's just data, right? It's just a bunch of observations that form a sample. So a sample is simply a set of observations from something. As Benton mentioned, that set has to come from a bigger set, right? And that bigger set is the population. So that is a basic 2023 definition of sample. It's collected from the population. Now, the formal theoretical way to represent this population is simply call it a sample space. Does it make sense as to why we call it the sample space?
It's the space where the sample comes.
It's the space where we collect the sample from, hence the name sample space. It's the same definition, but we call it a sample space because mathematics revolves around spaces, right? Again, analysis. So, if you took linear algebra or planning to, you will understand spaces. But the sample is coming from a sample space, in simple terms, or in practical terms, that would be the population that we all live in. Okay?
So the sample space is equivalent to population?
Yes.
Okay.
It's just the theoretical
Way of saying it.
equivalent of a population. I'll give an example in a second.
Let's go.
Of course, study here is the practical term, experiment is more of a theoretical term. Okay, so the sample space is usually denoted by omega, uppercase omega. And it is a set containing all possible outcomes of an experiment or a study. A simple example rolling a fair six-sided die. What is the sample state of that particular experiment?
1, 2, 3, 4, 5, and 6.
1, 2, 3, 4, 5, and 6.
Yeah.
Now here is the fun part. I want each of you to imagine that you have a die, in your hand, and you're rolling that die, and you see an outcome, and you're going to tell me what that outcome is. With me? Imagine a die, you're rolling that die, you see an outcome, you're going to tell me an outcome. And mind you, it is a fair six-sided die. Good? Okay, start with Peter. Go ahead.
3.
3.
1.
1. 2.
5.
5.
2.
2.
Oh, 6.
6. 2.
1.
1.
3.
3.
4.
4. And you?
3.
3. And
4.
4. Okay, plenty. So what did I just do? I took a sample.
Yes.
And every single observation that you guys gave me came from which set?
Omega.
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 Hence the name
Excellent.
sample space. I want you guys to connect the dots if you took statistics, what you must have, 2023. So the biggest set is what we call population. And the subset of that population is simply the sum. In the sense, every single observation that we collect here comes from that sum. Does that make sense? So every possible combination comes from the population, which is simply the sample space. Are we clear? Good.
Yep.
So now we have something called an event space. An event space is simply a collection of subsets of omega. Good. Theoretical definition. And by all means, the collection of subsets of omega will contain the empty set also. And not only that, if I define that event space, what letter should we use?
E.
E.
Okay.
Fine. E is good. Now, E is a subset of omega, right? Naturally by definition. This event space in and of itself is a subset of omega, or every single subset in E comes from omega. Okay. What's the taking foundations of math or discrete math? One of those. This is my sample space. I want you to write every possible subset of that set. Set containing 1, 2, and 3. Okay. Every possible subset of omega.
1, 2, 3. Empty set.
1, 2.
2, 3. 3, 2. 1 and 3. The empty set.
1, 2, 3.
And what is it, Benson?
The empty set, or the set with no elements.
Collection of subsets of omega, that is omega. I also mentioned that each event could be omega in and of itself. Yes? Do we agree that omega is part, or E is part of omega? It's right over there. And the empty set is always part of the event space. So every possible combination of a subset, so 1, 2, 3 individual elements, elements of 2, elements of 3, and so forth. In general, so in general, a sample space with k elements will have 2 raised k subsets, and that would include the empty set. In our case, omega was 3, so that k was 3. And the number subsets,
8.
2 raised 3, which is 8. Now, n, in terms of set language, it's the number of items in a set, going back to set theory, finite math. Number of items in a set is the blank of that set. Starts with C. Cardinality. So I could call the number of subsets that I have in my event space as the cardinality of E, right, in type thing. Guess we'll have to stick to this one because that one's easy. Let's say we have a three-sided die. There is. If you play Dungeons and Dragons, you'll know. Huh? There's a three-sided
You
die.
can simulate the one with six-sided die divided by two that's greater than three. But that's why. You can effectively have one, but there aren't actually three dice in there.
There isn't a three-sided.
I think it has to be
4, 6, 8, 12, 10, but not 3.
It's only three.
Also 20, also 20.
20, and then there's 56.
If you take a 6 though, divide by 2, if it's greater than 3, then it'd be 3-sided die, in fact, but it's not actually.
I have to look it up.
Does there have to be an even number of?
I got the dice in there, it's not with me.
So I have a four-sided die in my office. That's how I make decisions in life. And my favorite number is 2. If I have a situation where I can't make a decision, toss that die, I get 2. Go. Right.
It's called coin. It's like,
One of these days, you know, I might have some sort of major surgery and I'm scared and they toss that die. Can you give me a 2? What type of surgery is that? Okay, moving on. Let's say this is a three-sided die. The reason why I'm going with this because it's a small example. I'm going to define an event. I'll call it E1. E1 comes from E. E1,
so just not roll one. So just not roll one. Just not roll one.
the number greater than or equal to 2 does not involve 1 in here. Okay, sweet. E1 is a, yes,
We just define an event as a situation, correct?
yes. So E1, that's where I'm going.
Okay.
Trying to connect something practical with something that is theoretical. So you can see as when I started with sample space. I connected the sample space to population. Population is where the sample came from. I showed you how to pull a sample, what you guys did, from Omega. And we wrote the cardinality of each. Now I have an event that I'm pulling from the event space, and which in practice, or in practical terms, I'm going to say number greater than or equal to 2. Yes? What is the answer?
2.
2?
Or and others, but yeah.
3.
You put in that same set notation, it's like set contain.
Yeah, 2 and 3. I see what you're saying. So E1 number greater than or equal to 2, and that set is simply the elements 2 and 3. Do you agree? So is that a subset of E? So the event came from the event
Space.
space. I can keep on defining as many events as I possibly can. Right?
Yep.
So E1, E2, E3, you know, they're all subsets of E. I could take the intersections, I could take the unions and whatnot. So 2, 3 is a subset of E. Oh, okay, that's what is the cardinality of E1? 2. What is the cardinality of omega? 3. Here comes the rain again. Didn't get that joke? That's a song. 90s song by a band called Akira, I believe. I might be wrong. So the probability of the event E1, I do not know if the textbook uses P or PR. PR is formal, so if the textbook uses P, that's also fine, but PR is the formal notation for probability. So earlier today, I called probability as a measure of uncertainty, and I gave you a reason as to why we call it a measure. Do we remember?
It's a set number. Because it's a set, whatever set.
It's something that's at the actual set, right? And this particular operator, whatever calculation that we have, it is defined over sets. Do you agree? So when I say probability of E1, I'm actually talking about probability of set E1, which is, part of the event space, which is the bigger set. Do we agree? Now, how do we find that probability? That probability is simply the cardinality of E1 divided by the cardinality of omega. So, cardinality of E1 is 2. Cardinality of omega is 3. And, forget about all of this. Someone asks you, you roll a 3-sided die, what is the probability or likelihood that you get a number bigger than or equal to 2? What would you say? 66.67, which is 2/3. Like, that's 0.6667. But in terms of sets, it's simply the cardinality of the event divided by the cardinality of the entire sample space. If we go back to 2023 again, you can go back and look at your old textbook if you still have it. Do we remember that, fancy little definition? So that is, that standard definition that we used in, 2023 in intro to statistics. The number of outcomes in omega that favor the event E1 divided by the total number of outcomes in omega. In our case, total number of outcomes would be 3. The number that favor event 1 is 2. Does that make sense? Okay. Few things about probability. There are lots of probabilities, but I'm going to start with the simple ones for today. We are finding the probability of an empty set. It's the probability of an empty set. Now, this is a point where I'd like to connect theory with something in practice. We must always have that empty set in the event space of an experiment. It has to be there. Why? We know probability is a measure of uncertainty, and we're rolling a three-sided die, and every single event that I can come up with is going to come from here. Do we agree? And my question is, the empty set has to be there. Why should it be there?
Because nothing is always an option.
Because nothing is always an option. Who knows? You roll that three-sided die and all of a sudden it catches on fire.
Goes right off the table.
Right? Or you can't see. Or you roll that three-sided die and you're trying to look at the outcome and in that moment you go blind. Right? Very powerful die. So any of those could happen. So the empty set must always be a part of the event space. Does that make sense now? You should always account for that possibility of nothing happening because things are uncertain. Good. So the probability of the empty set would always be 0. And probability of the entire sample space has to be 1.
So that would solve.
Right.
Yep.
Now, here is, should we ask that question now? Okay, we should. I think I can erase this now. So suppose I have E1, E2, all the way up to EK. Those are all events in the sense they form some subset of omega. What would the probability of that, or some kth event be?
In between 0 and 1?
In between 0 and 1. Notice, I'll write it here. And I should probably say here, is of case a non-empty subset.
That's also not like
Suppose E1, E2, all the way up to EK are events in the sense they form a subset of, the event space E naught omega, possible subsets of E, which could be a subset or equal to big omega. There's nothing wrong with that. Proper to write it that way. The probability has to be between 0 and 1, but I didn't write it as 0 less than or equal to less than or equal to. Why?
Because it can't be 1 or 0.
Because it cannot be 1 or 0. Why? I want you to relate it to a subset.
If it's 1, it's the empty set, it can't be an empty set according to the rule.
If it's 1, it'll
So
be.
if it's 0, I'm sorry.
Yeah, if it is 0, then it would be an empty set.
Yeah, yeah.
Right, but I clearly stated that it is a non-empty set.
Yeah.
And,
1, it's omega, and it can't be omega. Because it's the-
and I don't want the entire omega either,
Yeah.
which is why I wrote at the beginning subset of omega and not omega entirely.
Yeah.
Let's tie this to something in practice, and let's see if it makes sense. Theoretically, we call it the probability of an empty set. In layman's terms, what would you call that event?
Possible. Nothing.
Go ahead,
Um,
you're close. I just didn't hear you properly.
my. So wait, so say that again, what was the question?
So probability of 0 is the probability of the empty set is 0.
Yeah.
That's a very subset-based,
Yeah.
mathematical expression. But in layman's terms,
It's
what would that event be?
Is it possible?
Impossible. This is the probability of an impossible event.
The flung, the sun flips inside out and expands.
Same thing. Probability of omega equals 1. In layman's terms, what are we saying? We are simply giving the probability of a certain event. What about the last case?
The probability of uncertain event.
Uncertain event? Well,
Kind of probable, I mean.
a probable event. So all of these, right here, simply the probability of a probable event. In other words, it could happen, but its probability is somewhere between 0 and 1.
Sure.
Before we end today, any questions on this? Yes.
So I understand your argument why probability of E of K is not 0, but why exactly can it not be 1?
Because it's the subset of omega, and I'm not including all of omega.
Okay.
So I don't want E of K to be equal to omega. I only want it to be a subset of omega.
Okay.
Right? So in all of E, there is omega, which is 1, 2, 3.
Yeah.
Right? So if EK is equal to omega, then its probability will be 1. How about this? Hold that thought for a second.
Okay.
Did you have a question?
Yeah, if you put the line underneath this.
Yeah.
That would make it where you would include.
Yes, if I put that line underneath, then it will include 1.
Right, okay.
Yeah. We all know this
Union.
unit, that
Intersection.
intersection. Now, we know summation, right? We know how to write summation I equals 1 to n. Same thing can be extended to sets. So,
Consider. One. There.
We do have E sub k is not equal, then.
would we have a situation where it couldn't equal omega?
No.
So you said that because, omega there's more than one event, the probability has to be sort of shared in between all of those. So one of them cannot take the whole of it. Does that make sense?
No. So what do you mean by?
I mean, because we were saying that it could have EK couldn't be one. So I was just thinking, it said that because there's many events in our sample set, not one of them can take the complete probability.
It can take the entire, outcomes 1, 2, and 3. That's what it couldn't be. So what I'm saying is I have all of these EKs, but none of those EKs will equal omega. In other words, I go back to the big E that I wrote. I can keep every single one of them, but I'm going to exclude the subset 1 to 3. So I'll only have 7 elements, right? We initially had 8. We get rid of, 1 to 3. Omega goes away. So what is the probability we have? It has to be between 0 and 1. You may ask me why I didn't put less than or equal to, because I said it's a non-empty set. So at this point, I got rid of omega, and got rid of the empty set. All I have is those 6 subsets. Good. Good place to stop. If you have questions, we talk to me.